So it seems like we're live. I'm getting all set up because I'm not in my usual place right now. So it's gonna just give me a couple minutes. And I think I think the connection should be a little bit worse, but I hope it's gonna be all good. So let me go to Stream Health. Let's go to Twitter and say I'm live at this here. And yeah. Also, if Slack would open, so it seems it's a bit slow, and we'll open basically the textbook as well. So got live. I'm live, not got live. I know I got a live. I'm live already, so perfect. Yep, we'll also actually go to Facebook and probably and do that as well. So quantum intuition, good. What are we doing today? QFT. I hope whoever's watching that that there's no quality issues. The voice might break, but I think the final recording should be fine. So I'm live. That's good. QFT. That's the QFT. Let's do QFT today. Okay, so I think we got everything here. Just let me close this stuff. I got one screen only. That's why I'm just, trying to set this whole thing up here. And we are going to go to the QFT. Now, I don't know if we're going to have time to do QFT and QPE. I thought QFT is worth diving in because it's got quite some nuances. I spent in the past some considerable amount of time digging into this. So I'm curious how the textbook deals with it. And it's tightly related to quantum phase estimation. But I think quantum phase estimation, it's big enough as well that it deserves another video. So I'll be checking back and forth. I'm sorry, the basically the YouTube live stream page, because it helps me see if there's any, and as I don't have a secondary screen. Okay, but let's get started. I mean, let's really get on with this. First, I'll open actually. Oh no, okay. Let's go directly to the QFT. Let's not lose time. So in this tutorial, we are going to introduce the quantum Fourier transform, derive the circuit, and implement it using Qiskit. I'm curious about the deriving the circuit. We show how to run QFT on a simulator and a 5-key device. Now, a word of advice here. So QFT is, I think, this is an algorithm that basically can be explained in a really confusing, with a lot of mathematics involved. That is just fancy notation for rotations. So let's see. Oh yeah, let's give it a quick. So we've got quite some content in here. Introduction. Example 1 qubit. Example 2 3 qubits. But I like that at least seems to go from small scale to bigger scale, and then hopefully some sort of general concept. Introduction. 1 qubit. The quantum Fourier transform, the circuit that implements the QFT. Okay. So as you can see, it's pretty heavy in the math here. But although just you should not be all the stuff that you see like exp, this is e to the power of all that stuff. This is just notation for rotations. So this is just and all this is saying is a phase rotation on the one component. So it seems heavy, but it's not that heavy. The 3 qubit example. Okay. the Qiskit implementation. Bum, 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 bum. Okay, let's see. And there's some problems in here. Okay, references as usual. I think that's feedback every time that we go through these. Yeah. So let's start from the top. Introduction. The Fourier transform occurs in many different versions throughout classical computing in areas ranging from signal processing to data compression to complexity theory. The quantum Fourier transform is the quantum implementation of the discrete Fourier transform. Is a quantum implementation of the discrete Fourier transform. So this is worth googling. Yeah. Okay. So the discrete Fourier transform. So this is basically as far as I know, a way to turn a wave, transform a signal, the signal of a wave, or sort of a wave, into its frequencies, or the set of frequencies that it's made of, and vice versa. So from the set of frequencies, you can then construct the wave. I think that's the whole point. Over the amplitudes of a wave function. It is part of many amplitudes. It is part of many quantum algorithms, most notably Shor's factoring algorithm and quantum phase estimation. Well, yeah, I mean, quantum phase estimation is Shor's factoring algorithm. As in, that's kind of the only quantum part, I think. I think that's the only quantum part in the algorithm. The discrete Fourier transform acts on a vector and maps it to the vector according to the formula. Let's okay. So where W? So again, those are. It's just a way to express a rotation, I guess. Similarly, the quantum Fourier transform acts on a quantum state of this shape and maps it to the quantum state of this shape according to this other formula. It's like that doesn't. It doesn't encourage me much to go for. Note that the only amplitudes of the state were affected by. Note that only the amplitudes of the state are affected by this transformation. This can also be expressed as the map. Why the amplitude? Only the amplitudes of the state. What do you mean by this? Is it just the amplitudes? Okay. I'm a bit confused right now, but let's move on. So, I know that the 1 qubit, I've read that somewhere, that the 1 qubit QFT is the Hadamard gate, actually, because the point is quirk. So if you apply a Hadamard gate, if let's say 0 is your input, and you apply a Hadamard gate, then you get that state, which you could think of. I think the way this goes is you're encoding your wave in the phase, right? So here the two elements have both phase 0. Now here, if I put in 1, then the phase here is like between this state and this state, there's a rotation of 180 degrees. And so it does kind of half a circle around the full phase, like the full 360 degrees. And so within your sample, it's done one cycle, right? Because the next element in that pattern would be again an element with phase 0. So that would be, I think that's the way this is. That's the way this goes. But let's go. I'm just confusing probably you more than anything right now. It says here the quality is good, it's not excellent. Um, but I can't really do better with the connection that I have here right now. Consider how the QFT operator as defined above act on single qubit state. Okay, so basically, I guess what this is going to go is this is going to go and use that to prove what I just said, that that it's a Hadamard. Okay, we obtain this state. Notice that how the Hadamard gate performs a discrete Fourier transform for n equals to on the amplitudes of the state. The QFT. So it's my point here is I think that it would benefit. It's a bit if you know coming from the other algorithms that are really practically. It's not that they are practical, it's that they are, I mean, the explanation is approached from a practical perspective. So you start with an example and there's a bit of math in there, but here this seems to me like it's pure top down, right? As in like that's the formula and here's the proof. And the quantum Fourier transform, so what does the quantum Fourier transform look like for a larger n? Let's derive a circuit for n equals 2 to the power of n, QFT n. Okay, so then it just goes boo, 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 having fun, and that's it. The circuit that implements the QFT. So the circuit that implements the QFT makes use of two gates. The first one is a single qubit Hadamard gate that you already know from the discussion in example 1 above. You have already seen that the action of Hadamard on the single qubit is the following. The second is a 2-qubit controlled rotation given in block diagonal form as the following. So basically it's a controlled rotation that applies the same rotation that the Hadamard would on the one component. The action of C rod K on the 2-qubit state, the second is the following. Yeah. Given these two gates, the circuit can be implemented. I guess where they're going is that if this is the final form, it's just a matter of concatenating these control rotations, right? Now this is this circuit operates as follows. We start with an n-qubit input state. After the first Hadamard, the state is transformed from the input state. So we apply Hadamard, and then this is the state that we have. Then we apply C-rod 2, and this is the state that we have, and so on, right? So after the application of the last C-rod gate on one qubit controlled by qubit n, the state becomes like this. And then it's like, note that this whole thing here can be written like that. Oh my god. Yeah, it's okay. Which is exactly the QFT of the input state as derived above, with the caveat that the order of the qubits is reversed in the output state. Oh, that's complicated to follow. How's it going? Suggestion, warning, all good, cool. An example to 3-qubit QFT. But why should I even do that if it's okay? So now there's the actual apply the Hadamard gate 0. Keep in mind the reverse order of the output state relative to the desired QFT. Therefore, measure the beats in reverse order. Okay. I'm already in 0.6, and a note about the form of the QFT. What I'm lacking here is I'm lacking a bit of context, right? I'm lacking a bit of I don't know, a bit of context of maybe the discrete Fourier transform and sort of how is this applied I don't know. It feels like it's a really steep learning curve. It's not a learning curve. It's like uh, if it was the first time I would read that, I'm like, what the hell is this? 3 QFT. Qiskit implementation. Let's get that. Let's get going then. In Qiskit, the implementation of the C-Rock gate used in the discussion above is a controlled phase rotation gate. And this gate is defined in OpenChasm as these as a CU1. Okay. Hence the mapping from C-Rock gate. Discussion above the CU1 gate is found from the equation. Okay. It is instructive. It is instructive to write out the relevant code for the 3-qubit case before generalizing to the n-qubit case. Okay, so we've got these in here. So let's just copy it. I don't know why this is not. So that's the generic case. Let me see if I can. Let me on the prompt. I just forgot to open the notebook. So I'll just go and basically go to the Qiskit reading group, and I think I should basically make session 5 and then go to session 5 and say Jupyter notebook and just okay, cool, and just get started with this. I'll import all the stuff anyway. So let's create a new notebook. And no, that's not here where I want to go. Wanted to copy these. What's wrong now? Math. Okay, it's probably not math, but NP. Or I can just use pi. I see in imports. I can just use pi. So I'll use pi. Q. Where is Q? Q is not defined. Hadamard. Yeah, that's I think there's some typos in here, so that should be just one if we're using the notation without registers. So that should be one. And if I do QFT3 draw output equals MPL, okay, that's what we have. So let's take a look and build that in Quirk. I've got a Hadamard in here. Then we've got, so those are just phase rotations, right? That's what they said here. Those are just controlled phase rotations. So those are just control pi divided by 2, pi divided by 4. But these I can implement by saying 1 divided by 2 and 1 divided by 4, and then control them on these 2 qubits. Where am I? Then Hadamard another controlled phase with pi over 2, and then another Hadamard, and then another one, and then another Hadamard. Okay, so yeah, so that's what we got, zeros, and then it's just a superposition in here, right? Because if those are zeros, then none of these control rotations is activated, and then this is the equivalent of just having the Hadamards in there. That kind of makes sense. But so how's it going here? Okay, good. Yeah, seems all good here. Good. Yeah, I worry that the stream quality is not that good and that it breaks from time to time. Whoa. So, but should be fine. I hope it is fine. If not, I'll promise you to record a backup session on these. And where was I? Here. Okay, so following the example above, so we're just now generalizing already. So this is already the generalization on how to build that. But let us take a look at these for a second. So my point here is I'm missing a bit of the context on the inputs and the outputs of the algorithm. If I for me, it's clear that 0, 0, 0 gives you this kind of superposition in here. If I turn that into a 1, what does this even mean, right? Like, it's messed up. This is a bit messed up. No. Because that's the circuit of what I call the inverse of the QFT. That's another interesting discussion. What I wanted to do is let me play with this QFT, because we've got a QFT box in here. And if I apply not QFT, the inverse of the QFT, which is not what no. So what's the amplitude display in here? So I want to get, I'm a bit confused right now. Anyway, let's just go ahead. I'm confused because I've digged into this before, and but I just don't want to go straight with my intuition, and I wanted to really stick to the explanation in here, just not to, because I might be a bit biased here. So following the above example, the case for n qubits can be generalized as the following. So there's basically a bit of pseudocode in here. It just iterates over the qubits, applies Hadamard, and then after each Hadamard, it does another iteration, and it increments the angle in which we rotate. Increments or decrements, I don't know. So this is basically what it does. This is basically what these functions here do, or they seem to do. Input state. So this is going to prepare a special n-qubit input state for QFT that produces an output of 1. Then it goes through the QFT, and then it does the swap of the registers, because it gives the output. The output has the registers in the wrong order. I think that's what they were saying here up in the beginning of the chapter. So so we're gonna define these functions in here, and now let's now implement a QFT on a prepared 3-qubit state input that should return 001. Input state QFT circuit output 1. Okay, so this is the circuit that prepares this is the circuit. I think we can ignore this. This is supposed to give you an input state that we know will give you 1. But this is all a bit awkward. And now, okay, now generates the circuit and it adds the swap at the end. Whoop, I didn't want to show these. So here's a bit inconsistent because here we're doing these, but then we're not having the swap at the end, whereas here we're adding the swap. So I'd also think that, also imagine we would need to add a swap in here, to be honest, between 0 and 2. Yeah, because if I do these here as well, how can I swap? How can I swap? Where are you? Swap here. That's the point. No, that's all awkward. QFT1. I don't know. I don't know what I'm doing. That's all a bit confusing. So then running it on a simulator, what does this give us? So if we run it on a simulator, let's just do this. One zero zero. But I thought it was supposed to be 001. What? And it's 100. So I think we indeed see that the outcome is always 001 when we execute the code. Note that the reverse order of the output is 100 compared to expected 001. We expect this as well, since the output risk contains the reverse key. Yes, but I mean you're adding a swap. You added a swap. Then why you're? I mean, that's so confusing. How's it going here with the connection? It's going all good. That's really confusing. That is really confusing. Okay, and we're done, I guess. I'm not gonna go through the real device. Although it's interesting to see the results, but and what are the problems? The above implementation of QFT was tested by using a special input state, which should give you back 001. Implement an input state which should give you a 100 and then 101. Let me. Okay. Let me back up a little bit. So there's a lot of stuff that I could be trying to explain from what I know, right? But that's the whole chapter is really confusing, the whole thing, because you start with the mathematics. It's really abstract. It feels really abstract. I'm not saying that it's, it's correct, and it's probably correct the way this is expressed in here and whatnot, but it's not really friendly for someone who's trying to learn that from a computer science perspective. And I'm talking about that type of audience. That's kind of me, really. And so I think whoever is writing this, I think you should really you should really define the audience, right? There's a in the O'Reilly book, they do an excellent job explaining these. So they basically go in and they explain that the idea of the QFT, and I'll explain. Let's do it this way. Let's try to explain that with Quirk's implementation. Okay, so Quirk has two built-in gates, the QFT and the inverse QFT here. Um, and basically they are just, it's the whole thing packed in one gate. So it's going to help me explain a bit of the context that I'm missing in here, in here. And we have to remember this is a sort of a discrete Fourier transform. It inspired this algorithm. Was based on This is based on the DFT, so to say, which is basically saying that, let me see if there's some of these speeches in here, lower or something. Frequency. No, that's not what I want to do. So here you've got the maths as well, you see, also the rotations and stuff like that. It doesn't help me either. Doesn't help me either. So the whole point is let's take a look at the QFT. First of all, let's see if this is the one that I wanna. Yes, this should be the one that I wanna talk about, QFT. So pay attention what this box is doing, right? So you've got the QFT in here. I'll try to zoom so you can see this better. So you've got this one in here. If the input is 1, let's assume we're just talking here about inputs that are not superpositions. They're just like binary numbers, right? 0, 0, 1 is the number 1, and the output that we get is it's a wave that's encoded in the phase of your superposition that gives one full cycle. That's your input, is the one in here, right? So if we start with a phase of 0, then it rotates 45 degrees for the next element in the amplitude in superposition. For the next element, it rotates another 45 degrees, so it has 90 degrees, 135, and now we sort of at that point we've done half the circle, right? So now we are at 180 degrees, and we go forward minus 135. Minus 90, or 270 in this case, and so we are at this point here where we've circled. Like, if there will be another box in the superposition, this would already be 45 degrees extra on top of that, which would be again this one, right? So we've done one full cycle. So this is what the QFT is doing. It's basically mapping. If you give it a frequency, and I might be using the wrong word, but if you give it that one number, it builds you a wave and encodes it, and it encodes it in the phase in the phases of your superposition. So just to show you what happens with another input, right? So if you put, for example, 0, 1, 1, now we are this should give 3 times within the amplitude. Within the superposition that we have, we should give 3 rounds, 3 full cycles. So we start here, and then we rotate 135 degrees. Pay attention that this is already 3 times 45 degrees, right? It's like before, when we had just the one here, we're doing step by step 45 degrees. So when we do that, we're kind of, because we have to go 3 times faster, right? Like, we're rotating 3 times faster. So we're doing 135 degrees, then we're back here, and then we have already, in between the decimal 2 and the decimal 3, we've already gone through with the first cycle, because we're now back at 45 degrees. And so the same here and the same here. And so at this point, we've exactly also crossing the second circle, the second kind of turnaround, the full 360 degrees. And then we're here. We realize that the next step, the next box would exactly be this one, right? So we've done three 3 rounds through the circle. I hope that I explained myself well, and I hope that the the thing didn't break here with from a quality perspective. How much time? So we're like, okay, just 30 minutes in. That's good. So this is the way that I understand the QFT, and this makes it a bit closer to how could I say that? It makes it a bit more closer to real world applications, because that's what the discrete Fourier transform is doing. It's picking. So I'm not really, I'm not really usually mix up concepts with frequencies and periods and whatnot, but this is what the DFT is actually supposed to do. There's a really good video on YouTube from also three blue, one brown, I think, 3 blue, 1 brown on the Fourier transform. And that's and so that's a really good that's I think a really good primer for the whole thing in here. And I'm not gonna, probably shouldn't load this because I'm gonna break the whole bandwidth in here. That's a commercial. So you probably can't see this anyway. But basically, and what's nice about this video is that it explains and it maps the whole concept of what the Fourier transform is doing with actual rotations. It's a really nice video. I recommend you to watch this video. It's just, just giving that reference in there would make a huge difference. Doesn't have to be this video, but the point here is so it explains the concept, right? Like of you've, and they're all like different frequencies, and they all mix up into one wave. And so what you want to do is you want to know which component. So if you have a final wave like this one here, you want to know which are the waves that are that this is composed of, right? That's the utility of this whole thing. And this is used for sound processing and a bunch of stuff, but that's the idea of the QFT. So you give it that as an input, and then you get the phase encoded wave, right? And the inverse of the QFT is gonna do the opposite, right? So it's gonna, if you give it that thing as an input, it's gonna wrap it up to the frequency that it's made of. And what's cool about the inverse of the QFT is that if you give it a real data from a wave, from a signal that you're processing, it's actually going to give you a superposition of the different frequencies that it's made of, right? So let's try to, and I think that's this is something that this is missing the whole point. And I don't want to be too harsh on this, but it's like, it's the beauty of this is that here we're not even diving into that kind of outcomes, right? Like, so we're not even diving into the, let me show you. So if let's say we use that as an input, right? So we've got that here. So if I now apply the inverse of the QFT, here, so it's, we've prepared that input on purpose because we know that this wave is gonna should go back to 0, 1, 1, right? And it goes back to 0, 1, 1. That's what the inverse is doing, which is, I know it's kind of obvious. How could I I'm trying to think about if that would be cool to actually do an example in Qiskit with real wave data, where you would encode each of these things into yeah, that would be quite cool actually, but it's probably too complicated to pull off in an hour and a half. But that's the whole point. I mean, I what I could do here is, I could do. I don't know if I could mess up with this even more and do some. I'm just playing with, you know, doing some extra rotations here and there. For example, I'm just adding some more random rotations in here, so it's not a clean wave. It's a wave that's composed of multiple things, right? Um, I don't know. These maybe, you know, whatever. So imagine, forget about this first part here. Just imagine this is your input, right? Then you want to know what frequencies this is made of. Then you apply the inverse of the QFT, and you get that, which basically means that each of these. So what this is telling you is that in order to get such a wave, or that this wave is composed of, you know, a frequency of 3 with 48%. So this means that that's the highest contribution. But then you've got all the other different frequencies, with, of course, that contribute to the. Actually, this I don't know. This I don't know if the magnitude in here, the amplitudes, or the squared amplitudes, or the squared, you know, whatever the magnitude. I don't know if these really mean contributions, as in, like, you know, that contributes way more to the whole shape of the wave, but it probably is, because we've kind of started off with a frequency of 3, and then we've done a couple of minor tweaks. So it intuitively could make sense that this is sort of the biggest influencer in terms of how the wave is shaped at the end, and the other frequencies are just adding, you know, it's a bit of extra noise. If you wanna, you could see this way as well, and so that makes the whole thing, I think, way more interesting than just that. But maybe let's try to understand the circuit that's presented in here for the 3 qubits example. Okay. How's it going on the stream side? Seems like we got here some warnings, but everything seems kind of fine. Yeah. Okay. Cool. So let's try to unpack how this is built, really. And there are, I think. Let's take that as an example, because I also know that some people call the QFT inverse QFT. Some people use the names in sort of an exchangeable way. Some coffee. What I mean is, some people call the inverse QFT what other people call the QFT. So I'm confused myself. An actually interesting fact here is that's pretty cool. If you let's clear that all. If you apply a QFT, let's say we've got a 3 here. If you apply, sorry, the inverse QFT, no, the QFT. If you apply the QFT, like I think it was 3 times, is the same as applying the inverse QFT. So this is QFT, right? If I now apply the inverse QFT down here, I'll just use 2 different amplitude displays so we can see, so we can compare them. So ignore this big one, because this is for the whole system. Yeah, so you can see that's an interesting thing as well, and this is because of the cyclic nature of the QFT. And really, the only difference between the QFT and the inverse QFT is that the rotations are done clockwise or counterclockwise. So, but let's get into this first, okay? Because I really like this algorithm, and I think that this doesn't do a good service for explaining the algorithm. It's just to the point, and it's probably mathematically correct, but it just lacks a lot of things that might make someone reading these for the first time actually really interested in this stuff. So QFT, good. Let's clear that all. Let's see what's up here. So let's take a look at that circuit and yeah, and let's implement it in Quirk. I had it, but I lost it. So we've got a Hadamard gate in here. We've got a controlled phase gate of 1/2. I'm not using pi over 2 because this is a control Z. If I kind of realized that if I use these, the RZ, I should then use an angle to express the rotation. But with the Z gate, you get the same result. You just parameterize the Z gate as in like in amount determined by the formula of like how many portions of a half cycle you want to do. But maybe, okay, maybe let's stick to the RZ just to be fair with the with these pi over 2. But actually, I don't know if I'm still not fully convinced myself that this is really what it should do. So what if I do, no, you see, it rotates the 0 component as well, and that's not what I want. I should 102. Yeah, I should get my hands on this difference between the RZ and the. This is just it's just bothering me so much. The RZ gate also rotates the 0 component, and we don't want these. Okay, so anyway, whatever. Let's move on. So 1/2, which I know it's basically an S gate, but let's stick to this so it's more visible what kind of rotations we're doing. Okay, then 1/4 and down here, and then we have another Hadamard gate, and we actually have the same thing, the same rotation like this one. And another Hadamard gate. So let's try to break down what the algorithm is doing here. First, let me try to figure out if this is the. So is this the one? So what is this implementation doing? Is it taking us from a frequency into an actual building the actual wave in this in a phase encoded wave, or is it doing the other way around? So I think this is actually based on the fact that the Hadamards are first. I think we're building the wave in here, right? I think we're definitely building the wave in here, but the trick here also is going to be what's going on with this, what's going to happen with the swaps, because let's see what happens. So basically, so the way that I would reason about this is let's put the display in here and let's see how this whole thing evolves, right? So we start with 0, 0, 0, and what we want to do, right? And let's try to play with the example of, for example, that we want, I don't know, one full cycle, right? One full cycle in here. So this is our input state. So we want this final result to give us one full cycle, and it's obviously not. So I think I missed somewhere here. I think I'm missing something in here. That's definitely not doing that. That's not doing that. That's actually the other one. So that's what that's the inverse QFT. That's the inverse QFT. I'm getting confused right now. If I from phase frequency space, if I give it a QFT of 1, But that's also not working quite well. I mean, even if I add the swap at the end, that's still not working quite well, is it? Oh, why is that? So the I'm trying to. There's something wrong with the circuit. There's definitely something awkward with the circuit. Pi divided by 2, pi divided by 4. I think it's not pi divided by 2. No, yeah, that's 90 degrees. There's something off with this circuit that I'm a bit confused with right now. So it starts off with a Hadamard. Oh, I think I see. That's not okay. I think I see. That's what I'm missing here is that I was right before. This seems to be constructing the wave. It's just that we have to add the swap at the beginning. Yeah, we got it. You see? Yeah, that's it. Of course. So let me walk you through my thought process. The thing is the following. So and you can construct that circuit differently, right? So you don't need the swap in here. The point is we wanna go from that input to that output, right? And so the way I'm trying to the thing is I'm trying to do this based on the circuit, and that's why I have to do a bit of an extra stretch, because this one in here, right? This one in here basically is if we so this one in here has the reason that I'm doing the swap in here is because if we've got a 1 in here, it means, right, that we need to basically do a full cycle. So my assumption in here is that the 2 halves, sorry, let me, the 2 halves of the superposition should be kind of mirrored, right? Because if we want to do 1 full cycle, it means that with our first half of the superposition, we have to have done already half the cycle, and then the rest is just a mirrored version of that, right? So we start here with a phase of 0, and pay attention that the first element of the second half is already a phase 180, so it's kind of already the mirrored version of that, and then each of these components are like a mirrored version of their counterpart on the other half of the superposition. So what you want to do is you want this number 1 in here. You want this number 1 in here to actually create that mirror by applying a Hadamard in here. So this Hadamard is not going to be but how do these rotations happen, really? Do they happen? So if I do this here, yeah, well, of course, the Hadamard does happen, right? Because this is then a 0 after the swap. So here, if we take a look at the block sphere, it's a 0. Yeah, so that Hadamard is going to basically double the state like that, right? So the rotations won't do this first rotation won't do anything. The second rotation will rotate that component by a fourth, right? Because those rotations are then a function of the weight this number has in the binary representation, and that's the point, right? So if we then the second Hadamard is going to double as this state, and then when you apply the second rotation, here, it's going to rotate. It's going to add 90 degrees to those two states because they have a 1 in the middle qubit. But because this one already was rotated, right? It was rotated here because when we applied the Hadamard, that pattern got duplicated. So this already had a rotation. So when you're adding 90 degrees to this one, it just accumulates it, right? So you've got at the end here, you've got that pattern of a half cycle, right? And so the last Hadamard, what it does is it mirrors this up to the rest of the superposition. So it's like you can see the QFT as a mechanism to what it does is it takes that number 1 and it unfolds it somehow, right? I mean, somehow by doing those rotations and applying Hadamard gates, it unfolds that into the particular wave, phase encoded wave that we have in here, step by step. So, but you need that swap in here because you want this number 1 to, I mean, this number 1 basically that's what it means. You want a full cycle, so the half of the superposition has to be half a cycle, and so you do this half cycle by like triggering these two control phase gates in here, and then the last Hadamard kind of doubles that up for you. If we would have, or we want to have, for example, four cycles, right? This is really sort of the yeah, that's basically this, right? Because you're going from 0 to 180, then back to 0, 180, back to 0, 180. So you're doing this 4 times, right? So in this case, this one kind of gets swapped with a 0 up here, and actually that's all you need. The rest is going to be basically the Hadamards are the only gates that are going to have any effect, because this one doesn't have any effect, this one doesn't have any effect. Then the next Hadamard is going to just copy, just gonna double that, yeah, and that doubles the whole thing. So that's how you get it. If you want to have a 7, so that's like the number of qubits, of course, determines how much granular you can go, right? So if you've got 3 qubits, it means that, well, if you would want to do 8 iterations, that would almost be like, it's the same like doing 0 with your precision, because you can't really go farther or past that, right? So 7, it's already the extreme where we've gone from here to here. So it's like the next one would be already, so we've done already one circle, one iteration in here, have we? Yeah. 1, 2, 3, 4, 5, 6, 7. Each is like, each element is giving a full rotation, so you get the 7. Yeah. So that's really what it's doing, but it's missing. So it's missing this swap for this to make sense at all. I mean, how's it going here? Health-wise, all good. My point here is that because of this state in here, let's prepare that state. So what's that state? Let me prepare that state. Let me open another quirk, and I'll prepare that state. And by the way, that's actually a bit confusing, because I thought that circuit, so that here they use the circuit to go back to, so this should give you 0, 0, 1 at the end, right? It's all in all confusing. So we've got this state in here, and now I'm going to add minus pi over 2 minus pi over 4. So I'm going to, this is basically minus pi. Oh, sorry, minus pi would be minus 1 in this case. And this would be minus 1 divided by 2, and this would be minus 1 divided by 4. Yeah, and that seems suspiciously swapped. If I swap these things, here you have. So this is, if you pay attention, if I change the signs to like plus, so I did like the inverse of these, right? Look at what we have here. So we have exactly, we've got exactly that one full cycle, one full rotation that I talked about. This is the, and so that is purposefully, I don't know what's the word, that state preparation hides already a swapping that just, it just obfuscates the whole thing even more, right? But let's assume this is the state that we have, and now let's see what happens if I put in this circuit in here. So but you see, there's something's kind of off in here, because I would do this totally different. Like if I add a Hadamard in here, because how would I now turn into a 1, right? So what you want to do, right? What you want to do, that's the base of the QFT, of the inverse QFT. So let's try to say, so the inverse QFT would be, let's take this into the actual 0, 0, 1 state, because that's frequency 1, right? It just gives one full cycle. So what you want to do in this case is you want to say, okay, so first, let's apply the thought process that we did to do this here, but backwards, right? And remember that here we're saying, okay, so these numbers have a certain weight on how these rotations are then applied. And we said if this is our starting point here, so what's the timing, by the way? Okay, 10, plenty of time. If it's a if this is the timing in here, if this is the the input in here, this number 1 basically means that like half the, so within half of our superposition we have to do already half the cycle, and then the second half is just a mirrored version of it. Whereas if we would have a 2, right, in here, 0, 1, 0, pay attention that there's no such mirror effect. Actually, it's easier to explain, because if you see that, if you can see there the exact copy, like, of course, because you have, oh yeah, now I remember the way that I reasoned about this later in earlier in some of my videos. If you've got like a 0 and the lowest weight qubit, it means your number is going to be even, right? So this means you're going to have an even number of cycles that you want to represent, which kind of essentially means that your second half of your superposition should be an exact copy of the other half, which, you know, that's just what the Hadamard does. Applied on a 0, it just kind of copies the phase, right? It's if you apply a Hadamard to 0, it turns into the 0 plus 1 state. So they both have the same phase. But if you apply it to 1, it takes you to 0 minus 1. So it's basically mirroring your phase. So this is, you're only kind of scaling that effect in here, right? And so I would go about this in the same way. I would say if I do a Hadamard in the last qubit in here, that should tell me whether my final frequency is even or odd. Because pay attention that the cycle here mirrors, right? So if I apply Hadamard, now if I take a look at the block sphere here, I see that it's a 1, right? And this is exactly that effect. This is exactly that effect of we've those things are mirrored, right? If how could I do or let's do the following. Let's just let me do the same that I did here, so we can take a look at the cases, right? So ignore this big display here, just focus on this one first. So if we're gonna apply A2 cycles in here, so if now I would apply, and those, imagine those things are equivalent. So this QFT basically, it's just creating that phase encoded wave in here. If I now apply a Hadamard here, and I take a look at the amplitudes again, of course, pay attention that it has the opposite effect, right? It takes the whole, it leaves the one, it leaves this half empty. It means that if I apply a block sphere here, I'll see that it's a 0. And this is because this Hadamard is picking up this pattern of whether this half of my superposition is a copy of this one or it's a mirrored copy of this one. So that's the effect in here. So that's how I would do this. I would basically do this here, right? But then in turn, I know that at the end of my circuit, I will want to swap these, because I know that this element or this qubit is gonna then be the lowest. So it's gonna be the one that's like on the rightmost side of my number, because it represents the parity of that number, right? How's it going here? It's going good. Ah, excellent, cool. And so the same thought process kind of applies, but now applies to the other qubits, right? But I would need, so I would still now need to apply some rotations, because yeah, because basically now I want to know so, but how I would apply the rotations? Would I apply them I would probably apply a 1.5. I think so, because that's gonna, so let's see what this is doing, right? What is this doing? Because that's picking up that's try to think about how to reason about this in an intuitive way. So so now I know the parity of this number, right? Now if this is a 1, so if this number is a 1, now I wanna basically I'm missing the intuition here a little bit. How would I because when we're doing it this way, right? So if here we've got a 1, right? So what we're doing is this 1 basically goes all the way here. Um, it does really like there are 2 rotations applied. The first one is a quarter, then there's a Hadamard, and then there's a half, because you want to build that circle in here. But the reason you do that is because if this would be a 1, it's got to do with the party of this number as well. Because if this would be a 1, then you would want these things to be mirrored, because it means you need to rotate even more. But essentially, I would reverse it like that. So I would say here, if this is a I would do a what do I say, a 1/2 rotation for these, and I think with Quake you can do that like 1/4. And so now we got at the stage where we've got the same like pattern. It's either going to be mirrored or it's going to be the same. If we I like to do this with the 2 different options in here, so we can basically take a look at how this would be different when there's a 1 or a 0 here, right? Because remember, this is 0, 0, 1. This is 0, 0, 1. Like if I take a look at the the chance, I put a chance display in here. Oh, sorry. That's not what I wanted to do. Whatever. This is the phase encoded wave with frequency 1, and this with frequency 2. If I now apply the same things in here, what's gonna happen? So this and this. So what's the pattern we get? Here we get that part, right? Opa. But here we already got, okay, so here there's no rotation that needs to be applied, because we've already got that that symmetry that we want. The only reason being that originally there's a 1 in here already. I'm convinced I've explained that better in the past in my other videos, but I can't now. I can't really figure out a more intuitive way to say if the party that we found is 1, then we still need to apply these rotations in here, and then another Hadamard gate would kind of again pick up the same pattern, right? Like, so it will basically tell us whether it's a 0 or a 1, and so we see that it's a 1, and that's a 1, and that's a 1. That's weird. That's weird. That's weird. because this should be 1 really. Hmm. 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 That's not what I was expecting. Uh, that's not what I was expecting. I might be doing this in the wrong way, I think. I want to get it right. It's just how's it going here with this? Okay, quality good and stuff like that. What I would assume is that I would now kind of do the same in here and then apply another Hadamard. That's the way that I would. Yeah, but that's not. No, no, no. I'm doing something wrong. I'm doing something wrong. So I'm wrapping it up like that. Because that's giving me 1, 1, 1. That's not what I want. Or should those rotations be backwards maybe? Yeah, 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 yeah. The rotations are backwards, or should be backwards. Why? Because now I have these, and now obviously once I do the swap at the end, because as I said, like the the parity of this number is then directly mapped to the value of the rightmost qubit, so it needs to be swapped in here, and then yeah, the one in the middle stays in the middle. Okay, so but what's going on here? So if I take a look at the amplitudes in here, let's try to that's the piece that I'm missing. So let's try to understand intuitively that step. So why do we need to do? Because I mean that's the same as doing 2 separate rotations like that, right? So this is just notation. So and in theory you could even do the Hadamard in between. That doesn't really matter because that's how it's constructed in here. But intuitively it seems, for me it seems to be more intuitive, like that you do all the rotations you need at once. So the Hadamard here picks the pattern. Okay, the last so this picks that, you know, whether that cycle should be mirrored or equal. Now you need to do over 2 and over 4. So let me get rid of this. It's gonna, oh, that's gonna help me maybe see things better with less mess in here. Yep. So so how I'm trying to reason about these the way that we've done it here, because these here the rotations are applied in a funky way, as in like accumulating the. So what's the role of the role in here, right? Let's say that we have, for example, a 1 versus like 3 or so. So this 3, what is this, or a 2, right? So what this 2 is going to do is, this 2 is going to basically, once you're done here, so it's going to activate that, rotation, because we know we want to do 2 cycles. half in here. This is not going to be activated, and then the Hadamard just copies that over. Essentially, yeah, and essentially basically letting that guy do the rest. Because what's the difference between these or these? What's the difference? So this adds another no, this adds another rotation in here. Because I think the intuition here is that the higher contribution qubits in here basically have the same influences in the sub systems, right? In the sub in like within the half of a rotation. So if we, it's like imagine. Okay, so imagine. I think I know an intuitive way to see this. Imagine. So we understand the the qubit that's on the rightmost side. It's either odd or even, and then that parity tells you about the nature of the two big halves of your superposition. Now, once you've once you've decided on these, then you can basically get rid of these qubit and then just focus on the superposition that you have, and then think of the other two numbers as the only inputs that you're gonna. I'm so bad at explaining. So what I mean is that now if we got a 0 and a 1 in here, we have to now imagine that what we want to do is we want to have one full cycle within. We want to have one full cycle within this half. Exactly. And so what that qubit is going to do is gonna, if we want one full cycle, right? So it is going to, yeah, you have to, it triggers this rotation in here that basically that's like a 90 degrees rotation, and then the Hadamard just copies the copies over the pattern, but in a mirrored way. Perfect. So this is exactly what this is what this is doing. So you need to, in order to pick up so each qubit represents the parity of a sub cycle inside your full. I don't know if I explained myself well. So once we know the parity of this qubit, then we basically need to rotate. We need to rotate the other ones as a function of these, right? Because what we're saying is if it's 1, because if it's 0 essentially, then nothing happens in here, right? Because if this is 0, how's it going, by the way? It's going good. 1 hour and a half through. So so if the parity, we've got the parity here, if this parity is 1, right, then we know, but why do we need a control on this? Cannot we build it? Can I not build it this way? This needs to happen, because this needs to be undone. These two rotations need to be undone. Because we're doing basically the reverse, right? So it's an uncomputation. So these two things need to be undone. And the reason this is done is because if it's a 1 in here, you go down here. So if we know the parity is 1, we're gonna have that. Okay, but we still need to have these rotations that basically do the actual. They actually build the first. They build the first rotation, so you need to undo that. So that's why you're controlling on the parity. because if this is a 0, basically these rotations don't happen. It's tricky to work out at the intuitive level, right? But it's really I think this is a much better exercise than the way this is explained in here without any of this context. Yeah. So then you control based on this parity. You undo these rotations. That's why they are the inverse of the z. Okay? So they are like -1/4, -1/2, and then this unwinding. So this kind of counterclockwise gives you with the pattern ready to catch of whether the parity of this qubit should be, whether the parity here should be, odd or even. So 0 or 1. Yeah, and then you do the same with the last qubit. So, and apologies because this is really messy with all this stuff. But basically, that's how I would do this. So that's how I would build this circuit that gives me 1. What I don't understand is why is this circuit that's supposed to give me 1, why is not giving me 1? That's what I don't understand. Let's try to, maybe let's try in Qiskit. So this is supposed to give me 1, right? Have I tried it in Qiskit already? I forgot. Oh yeah, but it does here give me 1. Or 1, 0, 0. So what am I doing wrong in Quirk? Let's clear all. Let's try to build it in Quirk. So we've got all Hadamarts. Then we've got parametrized rotation. So minus pi is -1 essentially, and this is -1 divided by 2 and -1 divided by 4. -1 divided by 4. I know why it didn't work out, because it didn't work out because I was swapping this stuff. Could it be? Because this is God. That's why this is done like that. It's okay. So this is not. I don't get it. Why? So this whole live stream is probably me just saying why. Okay, let's just go ahead and implement that. So there's a Hadamard gate. Yeah, now it peaks the pattern. Okay, so it does it like that. It's so awkward. Oh my god. I mean, that's completely counterintuitive to me. That's why I ended up building this in as you could see, the way that I built that was different, right? Because I built it under the premise that I had the input in a way that made sense to me. This input is like, it's got like you would have to swap this for this to make sense, as in you're rotating around these and giving it like a full circle. But this swap is not in here. It's kind of in a different order, and then you do these rotations, pi over 2, pi over 4. Bum, 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 bum. Pi over 2, and here it's going to be over 4. And now, yeah, now you see you've got the same thing here, right? How's it going with this? Okay, so poor quality. I can't really do anything about it other than this is kind of going well. The connection is bad. I'm really sorry for this. So buffering. I hope it will get better. Maybe if I yeah, maybe affected, drop frames affected. So let me try to fix that, okay? So now there should be data coming in. Now this should be working. Yeah, back up. So there was a bit of a hiccup, I think. Sorry for that, guys. Hope the stream didn't really get interrupted anyhow. Had some technical problems, but I'll put some pointers into these and then maybe write down my feedback. Apologies for these. So okay, but it seems like now we're better. Now we're back into a healthy. Cool. Connection was bad. So where was I? So now this kind of starts to make sense because I had used here the swap gates, and so and now this is doing exactly what I'm saying. It's kind of it's picking up the patterns. Oh my god, this is just so confusing the way this is explained. And then finally you got this, and now you've got the one. But guess what? This is a if you wanna. So I know that someone had a I mean, I complained, and some of the people were saying that there's a swap missing in here. And the point of the swap missing here is that, but if you add that swap in here, then you should also swap the input accordingly. Because now if I add the swap, it just doesn't make any sense. So if I do this, it's probably going to work if I do it this way. No, either. Okay. No, okay, I mess up. Sorry. That's not how it should be. So this is this in here, whatever. But you know what I mean? If I add a swap in here, then that's obviously not going to work. So then you gotta add a swap here as well, or change the way you generate the input. But it's interesting that doesn't work. Yeah. Yeah, well, it doesn't work because the circuit is it doesn't work because the circuit is tuned to the way this data is structured, of course. That's why you have these control rotations like that. That's yeah. So this needs to be definitely updated. That's definitely not working. That's definitely not working. So, again. Damn it. Poor quality. It's getting better now. I think I'm gonna stop here because I'm having some network issues, some big network issues because I'm at a place where I don't have so much bandwidth as I really would need to stream properly. But I guess that has been enough insightful in terms of the QFT. So to be honest with you, there's not much more I could say. I mean, I will definitely point you to the playlist where I break down that seriously deep and I go through all the stuff that we've gone through now. It's just, I think because of the lack of context, things can easily get lost. And I think someone added this swap in here that shouldn't be in here. This is really obscure the way this is prepared, and the fact that you're just told this is supposed to return 001, so go ahead and do this. But then because of that mistake, it returns 100. I don't know. I think but that's basically what it is, right? It's nothing else than you take a number, a frequency, and you try to make or build a wave out of the encoded in the phase, and vice versa. You get a wave that's encoded in your phase, and you kind of wrap it up in a way that in the reverse, like sort of in an inverted way, and in a way that it gives back the number that represents the frequency that makes that wave the way it is. And what I haven't shown in here is that of course works linearly for a superposition of frequencies. So if I have a how is the okay, so we're kind of back in with good quality, but so if I'll just show you this one last thing. So if I make a superposition, how can I make a superposition of, like, for example, 1 and 3 or something like that? So if I say da, 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 da. Can I just do, for example, I'm trying to think. So if I do these and I do that, what do I get? Okay, so now I have superposition of 1 and 2. If I apply the QFT to these, or is it the inverse QFT? QFT. It gives me this phase encoded wave. If I apply the QFT inverse, yeah. So what I'm trying to say is, you can take that as your input, and that builds a wave, and it encodes it in your phase in a way that it's sort of a contribution. It's sort of a mixture of a wave of frequency 1 and a wave of frequency 2, and that's how you get that thing in here. It's probably a bad example, but my point is it works with superposition as well. Of frequencies. And yeah, I think that's it. I'm going to leave it here because I see that I'm having some network issues, and I don't think it's worth for everyone else to take a look at this. I'll point to the other videos, the QFT, in the Slack channel and also in Twitter, and I hope that helps the reader as well. But I think there's a bunch of things. This chapter needs a lot of improvement. And for the next session, because I'll still be here, I'm recording from Spain. I'll probably I will pre-record that because I'm going to be flying back to Germany, and so I wouldn't be actually able to do that. So live. So I'll probably I'll probably pre-record that and upload it and make sure that it gets published at 9 a.m. Or I don't know, it doesn't matter. I'll publish it earlier or later, we'll see. But we'll do that via recorded video, not a live session. And then we'll go back to the regular schedule, okay? Cool. Thanks for those who managed to follow a little bit. I apologize for the network issues, but that's, I think, the QFT is definitely, the chapter in here is definitely can be improved a lot, in my opinion, especially the example part in here and the lack of context. Yeah, cool. I'm gonna end the stream now, and yeah, see you next week.